Thank you, Jim, and hello, everybody. So today and in the next couple of days, we will be talking a bit about statistics and how it helps us in trying to do the physics we want to do. This is basically my background, and I think I don't need to go through this. You can read it. The only important information of these slides are at the end. The first one is that I'm not a professional statistician, and I never gave any original contribution to the field. So please bear with me. I just hopeful to be a half decent practitioner, because more or less when I was, your age, I had to learn it for my work, for my analysis, and then I got caught. I liked it, and so I studied a little bit. And the other thing is that, of course, in an online lecture like this, and with you, that I don't know exactly the background of each of you. It might well be that some of the things are too elementary for you, too basic, and some other are maybe too advanced. And so please feel free to write me at any moment during or after the school if you have any specific questions or clarification to ask, etc., etc. Sorry. Okay. So, so statistics, it has various possible definitions, but perhaps one that is relevant to our thing is here. So it's the science of learning from data by identifying the properties of a population of natural phenomena and quantify our corresponding knowledge and uncertainty on it. And if you keep statistics in mind, you can perhaps design better experiments or better data analysis and make the most of your observation. In addition, it does offer a structure to frame our result and to interpret it in a way that people that reads our scientific document can understand it. And we are all on the same page on the kind of message we give. This is also important, so to have a common language to communicate our results. And it touches various possible tasks, from simulating a physics process to measure the value of a physics parameter, find its uncertainty, compare one hypothesis, which can be a physical theory, against another, comparing one hypothesis against all possible others, etc. And all of these tasks have technical names in statistics. So you have point estimation for measuring something, interval estimation if your measurement is not a central value but is an interval, etc., etc., etc. So one possible additional difficulty here is that there is some technical lingo in the middle, but don't get sidetracked from that. Ask me if things are not clear. And I don't know how these lectures are actually organized on your side, but I like when people interrupt me during my lecture. If you have questions, you can do it, in the middle of my lecture, and this helps us to be more attentive and to not to wait asleep.
Yes, so people are certainly encouraged to ask questions, but if they don't want to speak, they can put them in the chat, and
okay.
I'll interrupt you.
Yeah, let me know, because I don't see the chat here in my screen, but that's because I don't know to use Zoom very well. But I can probably access it if I go to the top menu or so. Yes, I see.
But I'll be following, so if someone does ask, I'll let you know, Diego. Okay.
Okay. So perhaps the first question one might ask is why do I need statistics to do physics at all? I mean, why should I handle that? In fact, if you think about other sciences, if you think of an entomologist that is, exploring some remote regions, and they find some strange insects, they just look it at the microscope, and I don't think they need any statistics to, state and understand that they've discovered an anomaly, something that has not yet been described in the insect literature, right? So they do not need to make any histogram or sophisticated data analysis. You know, this is a case where one insect, or if you want to phrase it in our lingo, one signal event is sufficient to claim that you've seen a signal. And that's because basically background is zero. You know that background is zero and you know it's certain. So if you see a flying donkey, you don't need to do a sophisticated data analysis to see that you've seen something anomalous, right? But in our case, things are different because we do have backgrounds. We do have large backgrounds, and those backgrounds are not only large, but also not exactly known. For instance, in this example here, you have a toy distribution of some data and a curve that passed through them. And this curve is the expected background that one would expect in this distribution. And you see that the data seems to follow the expected background everywhere, except perhaps here in the middle region, in 20 to 50, where there might be some kind of a deviation of the data from the expected curve, right? So you have the data overshooting the curve. And so it's a valid question to ask, I mean, I'm only seeing background here, which I would expect to be distributed as the curve, or there is something else. And so you can, you can qualify this question with perhaps a fit, like in this case, and you see that, in fact, if you allow for some narrow structure in that region, you would see perhaps a better fit to your data. And so here, the challenge, one of the challenges is to ask yourself how my data are compatible with background, and how does it compare with a compatibility with the background plus some anomaly, some signal that might be there. So it's not as simple as in the insect example here, because you need a little bit more of a sophisticated technical and quantitative assessment. So we're trying to understand nature from observations that are blurred. And this is, particularly, I want to argue that this is particularly interesting now in this particular phase of high energy physics and perhaps flavor physics in particular, because it's similar to low-level perception processes. High energy physics advanced through the interplay of two approaches. One is so-called, theory-guided top-down approach. So you have a theory, and this theory tells you that there is a specific effect to be searched in a specific data. And so you try to collect those data and you try to look for that specific effect. And then there is also a bottom-up approach in which you have no theory because you're exploring some uncharted territory, and you just try to have the data telling you where and if there is an anomaly. So when a roadmap, when a theory is present and tells us what to expect, you only need little data to make progress because you know exactly where to search. And in a way, this was somehow the situation that high energy physics, collider physics in particular, had been enjoying in the since the 70s to the 90s, basically, or at least even after that, because you had, you certainly know the standard model. This is this beautiful theory that with very few parameters tell us exactly what to expect in many, many different places. And so our colleagues have been looking in those places and have been one by one found the evidences that confirmed the standard model under the form of W and Z bosons, top quarks, and finally the Higgs boson. So you have basically something that started at the end of the 60s and concluded in 2012 with the discovery of the Higgs boson. And so this completed the standard model, and somehow deprived us of the top-down luxury. Now we no longer have a theory that tells us where exactly to look at. We have many possible theories, which are all the possible extensions of the standard model that people propose, and we have to, we have to use data to see which of those might be favored by nature. And so this is, this can be qualified under the form of various, open questions. What you might ask, why 3 quarks and 3 lepton families, why the mass hierarchies, etc. But all of these questions basically tells us that we do not have a top-down comfort anymore. We need to have a guidance from the data, and in this particular situation, then perhaps is even more important to understand well how to better handle our data in order to make the most out of them. And that's why statistics, I think it's an important tool here, and somehow this is a further motivation for that. So this is my outline. We'll have a first quick recap of the basics, and then the difference between probability and inference, and then we'll go to the point estimation, interval estimation, role of the model, and nuisance parameters, which is basically the systematic uncertainties that many of you may have already heard, and then hypothesis testing, significance, etc., etc. Again, this is a selection that I think might be useful, but I don't know exactly your background, so please, if your favorite topic or whatever confuses you most is not here, please write me and we'll take it from there. So let's go to the basics. And this is an important slide. It's important in the conceptual, philosophical sense in a way, because it lays down the fundamental notions. We have to be familiar with these concepts, and perhaps the first one is to understand exactly what a random event is. So a random event is some kind of an event, so it can be a physical measurement or something else that has more than one possible outcome. And so the outcome is not predicted deterministically, so you do not know what you will get once you observe that event, but you know the probability for each of the possible outcome to happen, okay? And I know that I'm already talking about probability without defining it, but at this level, take it as a limit of a long-term frequency. We will discuss this later, okay? So then this event can be associated to random variables, which are its properties, right? If you can call it also variates in statistics, but in fact, or observables, and if you do an experiment, but these are the properties of that event, which can take different values depending on each possible outcome. And we call them here, and in the rest of this talk, we call them with the generic symbol X. So X is the random variable, which can take, of course, different values, X0, X1, etc. And like I said before, since I know the probability for each outcome, I also know the probability for each X value, which I indicate as P of X here. And so the outcomes, the possible outcomes, generate a probability distribution for X, right? At each X, at each random variables corresponds a probability, and therefore the set of the possible probability can be put in a distribution as a function of X. Now, a collection of random events forms a population, and the population is an abstract concept that indicates the hypothetical infinite outcomes from repeated experiment that has to be independent and nearly identical. So, of course, this is an abstract concept because nobody makes infinite experiments. I mean, And what we observe usually, the observed distribution are interpreted as random samplings of finite size from this parent distribution. Okay, so the parent distribution is the ideal probability distribution, is the one I would get if I make an infinite number of observation. In reality, we make a finite number of observation, and therefore we only see a random sampling out of this parent distribution. And one of the important goals here is to quantify the collective properties of the abstract distribution, the parent one, using the observed distribution, the one that we see. So this looks a little bit esoteric, perhaps, but it's actually easy. So you can think of it as in this sketch here, where you have a parent distribution that, as you see, is very smooth because it has infinite, ideally infinite entries. And then you have each of you doing an experiment on this particular quantity, and each of you will basically observe one of the small plots that you see circling here, the blue one, right? Someone will see this distribution, some others will see this on the bottom left, and then another on the bottom. And they are all different because they all have different statistical fluctuation with respect to one another, but the underlying shape is the one of the parent distribution, which is inaccessible experimentally, of course. And maybe you're aware of that, but you actually do it every time you make an histogram. Every time you make an histogram, you are taking into account this transition from observed to abstract parent distribution. For instance, if you look at this histogram here, which refers to the Higgs observation by the Atlas collaboration, you see that this histogram has various data points, these black dots with the error bars, and then you have the expected distribution, which are the color curves, histograms. Now, forget about the histograms and just let's focus on the data points. And the data points in these two histograms are basically the event counts that have been observed in each of the bin of the mass that is on the horizontal axis, right? So in the first bin here to the left, they observe one event. In the second bin, they observe 15 events. In the third bin, they observe what? I don't know, 18 events, etc., etc., etc. And that's easy, right? That's the data points are easy. Now you see that these points have error bars. And if we were in a in-person lecture, I would ask you now, what are these error bars? What do they represent? And someone will tell me, oh, these are the uncertainties on those data points. And this is right. But if I ask you to quantify, qualify better what this uncertainty mean, then some people might be still confused. Because certainly when I do the analysis and I observe one event in the first bin, I have little uncertainty that that event was actually there, right? I observed it, and there is no way that instead of being one, it could have been 2 or 3. I mean, I observe one, and it certainly have to be 1. And similarly for the second bin, I observe 15. There is, I cannot make any mistake there. It's 15. I know how to count event in a bin, right? So the bar here does not represent the uncertainty of what I observed, because what I observed is pretty sure in this case. But the uncertainty so the error bar represent the possible range of values that I could have observed if I were to repeat this experiment various other times. Because the 15 events I observe in my second bin, if I redo the experiment, might not be 15, might be 12, or might be 18, because there are statistical fluctuations. You remember, this is a sampling from a parent distribution. And therefore, the length of the error bar is there to represent the possible fluctuations that I would have in repeated version of this experiment. Just as in this example here in the previous slide, each bin may have different counts from one experiment to the other, even if they're all drawn from the same parent distribution. So the first part of this lecture is what we do to represent the data. I will go fast here because those things are probably known to all of you. So suppose that I have a bunch of raw data and I, table them down in a piece of paper. I have this large table, which is not very informative. You would agree with me, right? And assuming that all observations are made in the equivalent conditions, the individual sequence does not matter typically. And all the relevant information is contained in the frequency of each outcome. So I'm not really interested to know that 79 here was following 73 and 72 was following 79. Perhaps the only thing that matters is how frequent are each of these values, right? So I can collect the frequencies in this scheme here, which is still, it's already better than before. It already gives me a picture of what's going on, because you know that very high counts have very high counts have zero frequencies, and then you start having frequencies here, here, and here, and then the others are it increases at the middle, etc. But it's still not very intuitive. And therefore, I can plot this into an histogram. And you see immediately that the histogram gives us a much better picture of what's going on, right? It tells us approximately where the data are located. It tells us, what is the spread of the data. And it also tells us what is the shape of the data. So here is a short aside on the binning, which I'm not going to spend time on that. You can read that and then get back to me with questions if you're curious. But it's just the fact that many people feel very strongly about how one would have to bin the data. I don't think this is a very important statistical problem. As soon as the bin has enough statistics, enough entries, maybe 10 or more. And what is important conceptually is rather to understand that every time you bin a distribution, you're losing statistical information, because you lose the detail of whether an event, an observation was in the middle of that bin or to the right or to the left. You're just treating all the events in a bin equally. And this amounts to a loss of statistical information. So I've now put my data into an histogram, and rather than staring at distribution, I can start to be a little bit more quantitative. And I can look at a few simple quantities that can be calculated and tell me already a little more about what's going on. So one could look at the sample mode. So where is the peak, which is the value of the variable for which the population is larger, or a sample median, so the range, so the value that is such that you have an equal amount of values to the right or to the left, so lower and higher values divided in half, or the sample mean, which is probably the most important one, which is the arithmetic average of the values of the variable and gives us an idea of where the distribution is, basically. And then you can calculate this, and I'm not going to spend time on this formula, you know them by heart. So you have the unbin case, the bin case, but these are very simple sample quantities that tell us where the data are. And then you can also measure how your data are spread, because the mean does not tell you anything whether about the dispersion of your data. So you, in this case, you use the variance, and the variance is this formula here that some people might find it a little bit confusing, so it's perhaps easier to remember as the mean of the squares minus the squares of the mean. And the root of the variance is the standard deviation that all of you know, which is usually very popular as a measure of a standard measure of spread, basically. If you go into multiple dimensions, so if you, in this case, it's 2 dimensions, but you can go to an infinite number of dimensions, you can easily generalize the mean and the variance to estimate the location and dispersion of the sample along each axis of the multidimensional space. And however, here you add an additional useful concept that quantifies the relation between the different quantities on each axis, which is the correlation. The correlation is calculated from the covariance, and the covariance is shown here is the mean of the product minus the product of the mean. And it can be generalized to many dimensions, of course. And we prefer to use the correlation because the covariance has units, where the correlation is basically the covariance divided by the product of the standard deviation. And this is a unitless quantity, and it's called correlation, but it's actually the linear correlation by person. And here it gives me, this discussion gives me an occasion to set the record straight on a very typical confusion that one has when start thinking about these things. Usually correlation and dependence between variables are often confused. And you have to remember that 2 variables, X and Y, are linearly uncorrelated if the correlation between them is 0. But this condition is not sufficient to state that they are also statistically independent. So these 2 quantities are statistically independent only if their 2-dimensional distribution, f of X and Y, can be factorized into the product of 2 one-dimensional distributions. So f of X and Y is actually the product of G times H, which means basically that the shape of one of the distribution does not depend on the value of the other. And in other words, information from one variable does not provide any information on the other. And you have to remember that variables that are independent are also uncorrelated, but variables that are uncorrelated may still be dependent. And so you see here representation of correlation strength and sign in 2 dimensions. So you have very highly correlated things you see on the extremes, and then progressively less and less correlated until 0 correlation here. But you also have variables that are very much dependent, as you see in this slide here. And if you compute the linear correlation between them, it's always 0. So this is just an example to tell you that checking that 2 variables are uncorrelated does not necessarily demonstrate that they're also independent. And to demonstrate that they are independent, you need to do some specific test, which is shown here. So if you have 2 variables here, you see in the first plot on the left, X and Y, you have all of these black points that are the 2-dimensional distribution of your sample in this X and Y metric. And if you want to check that these variables are independent, the best way to go is to make 2 or more narrow slices in one variable, and plot the other variable for the events belonging to these slices, and check whether the distribution in the non-sliced variable are independent across the slices. And so you see here that I've representing two slices in the X dimension, and then on the right plot, I have the distribution of the Y dimension for those events belonging to these, narrow slices, and I see that they actually change, they move, and therefore these variables are not independent, they are dependent. And this is a test that, it's useful when you do an analysis. Sometimes you want to write a model for your data, a multidimensional model, and it helps to understand whether some of these dimensions are independent, because it helps you writing the model in a simpler way. And to check that, you usually do this kind of exercises. Another important point is that sometimes correlation is used to demonstrate or infer causality. And because, of course, in physics and Flavour physics, we are interested in the causes of the phenomena. So because those are what is relevant to understand what's going on and build scientific evidence for the problem we are studying. But unfortunately, statistics does not tell us anything about causality. It does not tell anything about if two phenomena are causally linked or are just coincidentally linked. So, however, when two phenomena are correlated, one is, intuitively tending to think that there might be a causality link in that. But the problem is more difficult than it seems, because when you have two phenomena, A and B, that are correlated, it can be that A causes B, and in which case you have causality. It can be that B causes A, and also this is a causal link between the two. Or it can be that a third phenomenon, C, causes both A and B. So here you have a causality, but it's a causality that is basically going through a triangular relation in which the important cause is actually missing because C is not observed here. Or it can also be that correlation is just a coincidence. And there are some funny examples about that. Oh, I have a chat thing. Let me see.
Yeah. So there was one question. I was going to interrupt you after this slide. On the previous one about when we do the checks in the other dimension, is there some optimal width for how one chooses? So if you, I think referring to the previous slide.
Okay. Well, I think I don't think there is an optimal width universally, but you can look at the two-dimensional distribution, and you might see, the scale of the variation in one dimension, in the dimension you want to slice, and then you probably want to take the slide in a way that it takes into account the scale of the variation. So if the distribution is, strongly varying in that dimension, you don't want to take a slide that average many of these variation. You want to stick, to respect the variation of the distribution. I don't know if this answer your question. Yes.
Yes, thanks.
Now you have the problem of getting rid of this. Okay, it's gone. So I was saying that there are various funny examples here in the paradoxes of causality and correlation. Oh, I have another question. Let me see. So how do I get? Sorry, I lost my. Yes. In the previous slide, if Y and X were independent, the two plots dotted and solid, yes, exactly. Yes, they should coincide. Yes, the distribution of one variable does not depend on the value chosen for the other. Is that clear? Susoban? Okay. So let me go back to the Play here. Okay. No, I still have the chat. Okay, now it's better. So, for instance, in a funny example, you can imagine that at some point in the very old times, in the prehistory, some prehistoric people would be wondering whether it's the sun that rises that causes the singing of the chicken, or if the other way around, if the fact that the rooster sings means causes the sun to rise. Of course, I don't think they were so stupid. Probably they all figured out from the very beginning. But there are other things that are different, more difficult to figure out. For instance, there is a very interesting statistics of the murder rate in New York City in the late 80s that showed a very impressive correlation with the number of ice cream sold. You see this plot here. You have on the horizontal axis, you have the murder rate. On the vertical axis, you have the number of ice cream sold. And those data points, the blue one, are actually showing a very strong correlation between these two quantities that are seemingly uncorrelated or completely disconnected. And so if you were to interpret this sloppily, you will stop selling ice cream, because you knew that that would have basically reduced a lot of the street violence in New York City. But of course, this would not have worked, because what we are seeing here is an example of the triangular case I told you before. So you have a third phenomenon, C. We are looking at phenomenon A and B here, but we have a third phenomenon, C, which is basically the temperature. The weather is good in summer in New York. It's hot, and people spend more time on the streets. And spending more time on the streets, it's also they party and they sell drugs, and so it's easier and it's more likely that different gangs enter in contact and start fighting for tar, for drug dealing issues. And so therefore the violence. But also when it's hotter, people buy more ice creams because it's good, it feels good when it's hot to eat an ice cream. And therefore you see this very funny correlation here. And there is a website where there are any kind of also coincident correlations, which are very, very funny. For instance, here you can see along 10 years, that there is a very strong correlation between the number of people who died by becoming tangled in their bedsheet and the per capita cheese consumption. You see, these two curves seems one on top of the other, but of course there is absolutely no connection between them. Or similarly, the divorce rate in Maine and the per capita consumption of margarine in the same years. You see again here a very funny coincidence of two curves. So this is basically a funny picture of this. Just give me a second. I have. Sorry, I had to tell my wife where I left the car yesterday. So let's now going to describe the data in a more quantitative way. And so we have learned that if we take our raw data and we make a frequency distribution of them, we have a more direct representation of what's going on. And then we notice that most frequency distribution in experimental science are highly regular. You don't have any crazy stuff with many different shapes, etc. Usually we're dealing with regular distribution. And also we notice that typically we have a lot of data. So if we increase the number of observations, the frequency distribution become smoother and smoother. And so they somehow start approaching the theoretical probability distribution that we are interested in getting the properties of. And so it makes sense to start thinking about what would be the ideal parent distribution one would have once the number of observation goes to very high values. And here we need to introduce the concept of the probability density function, which you probably are already familiar with. So this is basically the frequency distribution for the limit of infinite observation for continuous variables. And so it's a curve that you see here, which is a function of the observed quantity x, and the eighth of this curve at each point of x is basically a measure of the frequency of that quantity in the small interval fx in the small integral delta x. So as delta x goes to 0, the probability that x has values between x and x plus delta x is this differential expression here, f times delta x. So this is, you know, mathematics aside, this is a probability density function. And you have to remember that this is a function of the data, and it is not a probability. It's a probability density. In fact, it has units of x to the -1, and probability cannot have units, right? And the other important thing is that it's normalized to unity. So, of course, the area of this should be 1. You know, the possible, you know, all the possible outcomes should sum to 1. And you probably are familiar with this, but there is a number of a few simple probability density functions that occur frequently in nearly any statistical problem. So you have to be familiar with them if you're not already. So this is the Gaussian, the Poisson, the binomial, and many others that are then listed in this nice short document that I found on the web. Another important quantity to keep in mind is the cumulative distribution. The cumulative density function expresses the probability that the quantity of interest x is between -infinite and x. And it's usually represented with this big F. And you will see in a moment why this is important. Of course, so far we've been looking at one-dimensional distribution, but in general, this is a business that applies to multi-dimensional distribution. And here again, you have, unfortunately, to get familiar with a little bit of jargon. So if you take a two-dimensional distribution, which is the simplest generalization to multiple dimensions, and you have a two-dimensional distribution, which is represented by this colored ellipses here in this plot. Here, the two dimensions are x1 and x2. And you have to keep in mind 3 different PDFs that you can construct from this. The first one is the joint PDF, which is the full two-dimensional distribution. So this is a function of x1 and x2 for a given value of whatever theoretical parameter m. And the joint PDF, so basically it will be the analytical form of this two-dimensional shape here, you know, whose contours are these ellipses. And this contains the whole statistical information, and it basically expresses the probability that both x1 and x2 assume simultaneously values in certain ranges. Okay? Then you might be curious to know of what is the conditional PDF. So what is the distribution of x1 for a specific value chosen for x2? This is equivalent to what we said before about the slicing, right? Sorry, I got it wrong here. It's actually the plotting x2 in a slice of x1. I got it the other way around. So you restrict your sample to a narrow range in x1, and you plot the distribution of x2 in that range. And this is called conditional because you're actually imposing a condition in x1, okay? And then there is the marginal PDF, which is very important, especially in Bayesian statistics, which is the distribution in one dimension that you obtain after integrating on the other one. So if you integrate the joint along x2, you get the marginal PDF, which is also, equivalent to actually a projection, right? If you project in one axis, you get the marginal with respect to the other. And this is a language that is often used, so I suggest you become familiar with that. If you're not, probably you're already, but it's just a reminder, okay? So joint, conditional, and marginal are different things that express different concepts associated with different quantities of statistical information. And also the PDFs can be characterized in a similar way as we characterize our data before. For instance, if you have a PDF for a certain set of data, you can calculate the expectation value of any function on those data by just calculating these quantities here. And the expectation value of X itself is actually the average value, or you can also get the expectation value of X minus the expectation value of X to the square, which is the variance. So this is basically an extension of what we just saw about the sample quantities. These are quantities, similar quantities associated with the PDF. Now, one important piece of information here is actually to understand what happens to a PDF when one changes, make a change of variable, or takes actually a function of a random variable. So our random variable X is the quantity we are observing, and suppose that we know the PDF of X, which we call f of X. So f of X is the PDF of the random variable X. Now I would like to answer the question, what does it happen if I take a function of X, which I call y of X, and I would like to know what is the PDF of Y. So since X is a random variable, therefore also Y of X will be a random variable, just another random variable, and therefore it will have a PDF. And I'm wondering, how can I get from the PDF of my original random variable to the PDF of the transformed one? And this is actually, conceptually, is very easy. You have just to impose the conservation of probability, which is in this first line here. Basically, I'm imposing that the probability that X is observed between XA and XB should be the same as the probability of observing Y between the values of Y of XA and Y of XB, you see here on the right. So if you impose this with the definition that we know, you will write that the probability of X between X and A and X and Y is actually the integral of the PDF between XA and XB. Sorry, it was XB, not XY there. And this should be equal to the integral between Y calculated at the point XA and Y calculated at the point XB of the unknown PDF G, which is the one I'm trying to find, that is the PDF of the variable Y. So if you do a little bit of algebraic massage, you will see that in the end, you can extract G of Y as from this formula here. So G of Y will be F of X, the PDF I know, divided by dy over dx. And dy over dx is basically the Jacobian that modifies the volume element. Okay? So this is very simple mathematics. I'm sure that you know it much better than I. And the reason why I actually want to state this is because I want to use this to show you that the mode, so the peak of the probability density, is not invariant under the change of metric. So if the peak of the PDF of X, the peak of F, will be generally different from the peak of G, where G is the PDF of the transformed variables Y. And therefore, this will be important later on, where we will see that taking the maximum probability as a guiding principle in the inference is usually not a very good idea, because the maximum probability is only dependent on the metric I'm using, on the quantity, on the random quantity I'm using. If I use X, the maximum probability in fx will be somewhere, but if instead of using X, I was using a function of X, a different function of X in my experiment, I would have the maximum probability somewhere else. I understand that this now sounds a little bit obscure, but hopefully you will get that clear later. I see that I only have 5 minutes, so let me. A special case of this is when X is continuous, I can use as a transformed variable the cumulative of X. So what in the previous slide I called Y, in this slide is actually the cumulative. You remember the integral from -infinity to X of X. So if I apply the previous slide machinery to the special case in which my transformed variable is the cumulative of the variable itself, I get that the PDF of the transformed variable is the uniform distribution. Okay? And you might wonder, you know, why is that important? And is it important to convey the message that any continuous distribution can be transformed into a uniform distribution by just a change of metric? And so this has important consequences later on when we will talk about inference, because in some cases, especially of Bayesian inference, people tend to give a special role to uniform distributions, in a sense that they are thought to be, objective or non-informative. But this probability integrand transform that I just showed you here shows you that the uniform distribution has no special role whatsoever, because it just depends on the metric you choose. So you can always find a random variable associated with your program that will give you a uniform distribution if you want. So let me go to the most interesting part of this this thing, which is that, we're not, we now learn a little bit how to describe our data. You probably knew all of these things already. But what we do in physics is not just to describe the data. We want to estimate the physics parameters that underlie our data distribution. And please note that estimation in statistics is a technical word. It doesn't mean, giving a guess, an approximate guess. Estimation is a technical word. It means using the data to determine the value of a parameter and its uncertainty. And this is the realm of statistical inference. And statistical inference is very important because it's not actually as mathematically rigorous as probability, right? Except trivial cases, one cannot make any inference from the sample with the certainty of deductive logic. Any inference will be necessarily associated with the assessments of probability or confidence or uncertainty due to the unobservability of the whole population and due to the fact that we only see a random sampling of it and that the phenomena themselves are not a random, right? They are not deterministic. And so here it's not only less mathematically, I would say conceptually rigorous, but it's also unfortunate that statisticians here divide into two schools. And since two schools disagree on the first principles, which are mainly related to the notion and meaning of probability, then this thing branches out in two different, basically, approaches. And I will try to give you a flavor of both approaches here, and then you will choose yourself what is the most convincing for you, but it's important to at least know the concept associated and subtending to each. So first of all, statistics is the inverse problem of probability. The theory of probability is a branch of pure mathematics. It is based on axioms and definition from which one obtains deductively the propositions. The theory of statistics is essentially inductive and empirical because it attempts at inferring the values of some unknown parameters from the observation of events. And this is very important, right? A probability problem is like, find the probability of observing a certain number of heads when tossing a coin n times, knowing the probability of that coin to land head. And this is a probability problem. This is easy. It has no ambiguity in the solution. You can calculate very easily. A statistics problem is, a coin is tossed n times and lands heads j times. What can we say about the probability of landing heads? And you see here the inverse thing, right? In one case, you are deducing the thing, and in the other case, you need to infer from the result. And here there are, in inference business, there are three fundamental ingredients. One is that one has all the relevant information. One has to set up his experiment or his analysis in a way to be able to measure, to observe all the relevant quantities, which we call generically X. And one is hoping to use those observable X to identify some set of relevant unknown parameters of the theory, for instance, which we generically call M. And the third and most important ingredient here is that you need to have a model that for both. You need to have a model that connects the observation X with the unknown parameter M. So the model is a mathematical structure, which I identify here as, in this symbolic language, P. And this is the probability of observing the data given, this vertical bar is express conditionality. So given that there is some physics going on, okay? So the probability of the data given the physics, or in the language we just used so far, the probability of observing X given a theory parameter M. Okay? So the model incorporates all the physics, knowledge, and intuition to best describe the relevant relation between the observable X and the unknown parameter M. And you have to remember that this is a probability model. So in plain English, this means that you do not know exactly what value of X will be observed, even if you knew exactly the value of M. So even if someone tells you, that the mass of the Higgs is 125 GeV with, absolute certainty, no uncertainty, still, when you look at your quantities X, which might be the invariant mass of the X decay product, you will have a distribution of them. Okay? So you do not know exactly the value of X, even if you knew exactly the value of M. It's a probability model. And the width of this is connected to the statistical uncertainty of your inference. So you have to remember that the model is the fundamental building block of most of inference. And until here, the two statistics schools are together. They all, assume the model. The model is the basic assumption we all make to start our inference. Is the step that everyone agrees on, okay? I think I'm 3 minutes past the hour, so maybe this is a good time to stop and get some questions. I don't know what you think, Jim.
Yeah, no, this would be a good time to pause. Arancha's here, our next lecturer. Yeah, so, and I guess introducing the Bayesian and frequentist approach tomorrow will be a good place to start. So, just opening the chat. I didn't see any more questions.
Jim, may I ask the question? Amol here.
Yes.
Diego, hey, so you showed on one of your slides the distribution showing the case where events are uncorrelated but still not independent with those sort of probability distribution dots, no? The scatter plots. Can you go to that slide, please? Yeah. So for understanding that they are dependent, of course, I can understand by looking at them visually. But visually speaking, how can I figure out that they are uncorrelated? What is it that I should look for?
And I don't know. This is not easy. I mean, there are things that it's easy. For instance, in the case of a circle, or in a when it's uniform, you can visually see that they are uncorrelated. But in other cases, not so easy. But usually, calculating correlation is pretty straightforward. So you don't need to visually guess. You can just do it and be sure.
Okay, thanks. I was just wondering if there was a visual.
At least I don't know how to do. Maybe some people smarter than me know how to do it visually also. I don't.
Thanks.
There was a question on the chat. Yes, I will get you the slides later on. Later on today.
Yeah, if you share the link, I can propagate it.
Yes, I will. I was looking for an Indico page for uploading, but I didn't find. But I just did it quickly. Maybe I should do it.
No, there's no Indico. There's the ICTS who hosts this. They have their own website, which they'll put the slides on.
Okay. Is there any conceptual confusion on the things that I introduced today? Especially on what is the model, what is the, the difference between, observable X and theory parameter M? Because if there is confusion there, you might lose touch tomorrow. So it's important to be clear on this.
Okay. I don't see anything right now, Diego, but we should bear this in mind for tomorrow. This point is clear. So I think, Diego, thanks very much for today. I enjoyed your various cheese consumption things. I have a personal favorite of these, which is you can show that there's an anti-correlation between the number of pirates and global warming. So if you had more pirates, you would solve global warming. So, but anyway, that's the one I tend to show. Okay. All right.
Thank you, and thank all the students. We'll talk again tomorrow. Okay.
Yeah, same time tomorrow morning. So thanks a lot, Diego.
Bye bye.
Bye bye.